Okay, thanks. So let me just start by recap what we did yesterday afternoon, the main theorem, because maybe slightly ended with a little bit rush, so I just recap what's the structure. So the basically yesterday afternoon I was trying to explain the following theorem on this category of shifts on isoc. There's a full subcategory, which will be called the shift Tame isoc, and it was characterized by three equivalent conditions. One is if you the shift when you shrink restrict to each strata, which is it's a depth zero representation in the depth zero block of the representation periodic group. The second condition is when you start restriction to each strata, it's a depth zero, and the third one is it can be considered as a subcategory generated by the so-called horizontal transform. So it's a pull push from shifts on LG mod I plus, the pull back and push forward, where I plus is the pro-unipotent radical, and the shifts here are some so-called monodromic shifts, the torus aberrant. Okay. The strategy to prove this was we basically try to, like the first two descriptions of this categories are pretty concrete. It's just this, when you restrict each strata, is something we know before, like, and it's in classical representation theory. So representation through periodic groups, we know what the depth zero representations. The third one, the whole point is to understand the third category, those generated by pull push. These are kind of some complex object. And for arbitrary E, and then the strategy was trying to first reduce, to understand the category generated by these objects, we do a bunch of reduction to understand some particular E, not the arbitrary one. The first reductions, we can just consider those E come from some kind of the, we just need to understand the E of this form. So, oops. Yeah, this form. So this so-called co-standard object. And in this case, it turns out this pull push and restrict to each strata is just the cohomology of F-and-Lustig varieties equipped with the action of the periodic groups. So basically, we were trying to understand like what kind of representation of periodic groups could appear in the cohomology of those F-and-Lustig varieties. This is what we are trying to say, and then, then I was trying to, this remark was trying to say that in general this is pretty complicated, like this structure of the Lustig variety, F-and-Lustig variety is very complicated, and we don't know much about this for general W and B, but then there's a bunch of reduction at some point to reduce to show we don't need to really understand the cohomology of general F-and-Lustig varieties, but some very special ones. So this is some elements of this form, particular form. We just need to understand a cohomology of the Lustig variety for this W, which is from X times U, where X is some some very special type of element in the F and Y group, satisfying this some length condition on the length. So this is actually it's so-called the sigma strict element, and then U is essentially some element in the finite Y group, KW somehow determined by X, or maybe not uniquely determined by X, but sort of something attached to X. And for these kind of W, it turns out that we can understand the structure of F-and-Lustig variety. We can pretty much understand what's the structure, and in fact, we can understand more, not just the cohomology, not just the geometry of the F-and-Lustig variety, but the whole, this whole local Stuka attached to this element. It's written as it is just a finite Lustig variety modulo some like parahoric of this of GB this PKO, actually it's very more precisely should be this X sigma. It's fixed by X sigma when maybe take the brief. So this K determines some parahoric of this group over maximum unramified extension, and then you sort of use not the standard Frobenius structure, but the Frobenius structure twisted by this X that produce some parahoric of GB F, and then it turns out that the whole structure of the Stuka, local Stuka can be understood. And also I said that in this case, actually the whole Stuka basically just map to one Newton strata downstairs. So we can, using this actually, what we're seeing is we can basically show this subcategory using that structure is contained in, for example, in this subcategory. Okay, because when you look at all the stock, you get this, and then you need to do a little bit of work to show like 1 is also contained in 3, and there's also some equivalence between 1 and 2. So anyway, so that's roughly what we did in last lecture, to just give a characterization of different, the same category inside the ice of G. That's what we call and this is once we have this characterization, this is what we call Tame part of the local Langlands category. Okay, and by the way, this is a picture of F and the little ADLB. Okay, right. So, okay. So let's start on today's talk. So today we're gonna talk about how to the general maybe this as I said in the first lecture, to get the categorical local Langlands, the Tame part is where the yoga is taking Frobenius trace of some local geometrical Langlands and some for this some Tame version to get and to get a categorical one. So this trace construction was discussed last week in Arnold's talk. Like using this in the finite situation, this gives us the Stenoustic theory. It was also in the coherent setting, was also mentioned, I think, in Davis' talk. So maybe I think I will try to recap it a little bit and actually give a uniform treatment. What the David talked and what the Enor talked actually is just one theorem, not really two different theorems. But so I will try to say a little bit about this. So today's trace more on trace formalism. So I'm actually trying to give you a abstract way to compute certain the trace of certain monoidal categories. So maybe but I think it turns out I think the best way to do it is to start from, let me just start from some abstract shift theory or three-funct formalism. So let's start from some D, which is lax symmetric monoidal functor from some correspondence category to presentable lambda linear infinite categories, stable categories. So as I said, this goes as follows. So we have two classes of morphisms. One is called vertical. This is F, this is G. So this is a vertical morphism, and this is H stands for horizontal. So this can be, then from here you can pull back along horizontal one and push forward along vertical ones. So, you know, in this abstract setup, actually I changed the notation. The usual thing is, you know, as in yesterday in Lucas' talk, if you do the usual things, you pull back, we would start pull back and then push forward, shrink, push forward. But then if I would like to use some other notations, so then I could, don't want to, because I don't want to contradict with some more traditional notations. And in applications, this, you know, the start pullback could be any kind of pullback I want to put, and the stagger push forward will be any kind of push forward. As soon as they fit into this formalism, I can plug in. So this will allow me not to change the. And let me make this assumption that assume the following two things. This category, of course, we always assume C has a finite product. So there's a final object, which I didn't know by point. I assume this is a rigid monoidal. I think this was introduced last week in Arnold's talk. Maybe you only introduced in compact general ones, but it's very similar. It's you can also do non-compact generated ones, but yeah, you can safely assume it's compact generated categories as rigid monoidal. So, and let me, for simplicity, also assume the following thing is true. Is the tensor product, like this, some kind of conic formula holds in this situation. I want to say this is fully faithful. And for simplicity, I assume admitting continuous right adjoint. This is like an exterior tensor product. Okay, so I assume this is true. All right, okay. Then from here, this is just, I mean, one could do more general things, but these assumptions are enough for our applications. So now suppose I'm given some x. So let's say, suppose it's an object in C satisfying the following two conditions. Let me just write it this way. I use this. No, exterior tensor product is not. You don't need the star pullback. It's inherent into this. This is a Lax symmetric monoidal functor. Lax symmetric monoidal. Yeah, that's a structure included in this. And yeah, if you could take some, if it's x times x. Then you could, if x and y are the same, then you can further star pullback along the diagonal. That would give you some kind of a symmetric monoidal structure on dx itself. But here you don't need the thing. Yeah, so now assume, so now given f x to y. And I assume this is, I will make the following assumption, satisfying the following two assumptions. One is f itself is in this, you can push forward along f. So this is in V, meaning it's you can do push forward along f. And the relative diagonal, you can also push forward along relative diagonal. Okay, the second assumption is if I have the diagonal of X itself and the structure map, both are in H, that means you can pull back along diagonal of X and to a point. So in fact, this condition, see, once you have this, as I just mentioned, you can then endorse dx as a symmetric monodal category, has a symmetric monodal category structure. Yes, symmetric. It's a symmetric monodal structure. Yeah, because X itself becomes an algebra object in this category of correspondence set. But what we are really interested in not in this, is we are, if you think about all this construction, what we are really interested in this, want to consider some object like X times X over Y. So actually this actually is an algebra object under this in this category. Because you can, for example, the multiplication is going to be defined as follows. Yeah, under our assumption, we can pull back along diagonal of X and then push forward along F. So this defines a multiplication. And also we have a unit. It's given by pull back kind of along here and push forward along this relative diagonal. Okay, so this endorses X times X over Y as a algebra object, and therefore, you will see dx times X over Y is a monodal category. You have tensor product. So explicitly, let me just write down the monodal. The multiplication is just you have some two. This is kind of some shift. You have two shifts, F and G, inside here. The product, so-called convolution product, is obtained. You first take the exterior tensor, then start pull back along the diagonal. Actually, it's this, right? It's this 1 times delta. And then 1 times F times 1, push forward. So that's how this, let me just write down explicitly how this is, the monodal structure is defined. So this is the usual called the convolution product. Now more generally, now suppose I have another object Z equipped with two maps, G1 and G2, to Y. Suppose I have something like this. Then I can define, actually maybe, how does it go to here? Then I can consider the following. I can consider X times Z over Y times Y over X. So here is this G1 map, this is G2 map, okay? And then this is actually a bimodule over this algebra. There's a convolution act from the left and the convolution from the right, okay? So it's just as the definition is similar as before, because I can pull back along the diagonal of X and push forward from X to Y. Yeah, so you have this, actually gives this guy a bimodule, this category of shifts on this product space is it's kind of a bimodule over this algebra. So let me denote this by A. This is by F. Okay. Right. Okay. So now we have this structure. Then we can talk about the. I think this was explained by Arnold last week. So we can think about bimodule as an endomorphism of A in certain Morita 2 category, and you can take its trace. So explicitly it's given by some Hausdorff homology. So you can take this trace of F of, this is A module, this is kind of in some certain Morita 2 category. So whatever it is, it's, I don't want to recall its precise definition. It's also sometimes read as a Hausdorff homology of A with coefficient is bimodule, or maybe people would write it in this way when you write bimodule. I don't know. And more explicitly, it's just A tensor with F over A tensor with A up. So this is a kind of the definition. And then it's kind of and now the goal is I was trying to explain how to understand this geometrically. There's some abstract definition, just you know, this doing this. It's defined as this like this relative tensor product. In the sense of Lurie in this Abin symmetric monoidal category, presentable categories. But we want to understand this more geometrically, realize there's certain category of sheaves on certain spaces or some subcategory of sheaves. So then the crucial this, I was saying A is D, F is yes, yeah, okay. So that was so then the crucial thing is really all the business is this so-called horizontal diagram. It is this following correspondence. So I will consider the following thing. Consider X times Z over Y times Y. And I will just write it. Let me just write it down. So then this do X times X over Y times Y for Z. So this is X. If you think about it, this is just our I just rewrite this X times Z times X over Y times Y as this following form, and then this is receiving this amperance alert several times a day. Okay, this is a delta X times identity of Z. So, and then you just do F times identity of Z. Let's go to Y times Z over Y times Y. Okay, so this is really the basic diagram we need to consider, this horizontal. Well, okay, at the moment it's just some abstract, we're just manipulating some, you know, just some, yes, okay, then let me call this is delta. Let me call this Q, maybe delta 0, this is what I Q. So then one can easily, the following lemma is easy. I think this is some abstract version of some lemma, also Arnold mentioned last week. Is if you, geometrically you can consider the following thing. You can pull back, go to D of Y times Y Then you can push forward, Q, to D. Oops, here is X, it's crucial Y times Y over Z. On the other, and then geometrically you can do this, push. And the claim is this functor factors through the trace, so this is, we call this F, it factors through this trace of F of a module. This is some abstractly defined category, and it will factor through. This diagram is commutative, so this is some pretty abstract thing. We will make it, yeah, so far we're just manipulating some symbols, but later we'll plug in X and Y to different things, and we'll get something concrete, but this, I don't want to prove different, each time prove a theorem. It's just one theorem, and then you just plug in different, replace these symbols by concrete math object, you'll get. Okay, so this is this is a sort of easy to see. This comes from some universal property of, for example, trace construction. But I will, but if you want to see more, is how these bottom lines are related to each other. Then I need to make some stronger assumptions. So far, this is what you can see. But it turns out, yeah, this is, again, let me just write this way. In order to see something more useful related to something downstairs, I need to make assumptions. So for this, I need to introduce maybe let me just say the goal is to maybe the question. The goal is when the bottom functor is an equivalence, and it turns out this is too much to ask in general on this generality, but one can say something slightly weaker, or when it is fully faithful. So to ask something is equivalent in this kind of generality, to ask when the bottom functor is equivalences, I don't have any general criterion, but I'm going to tell you some general criterion to say the bottom functor is fully faithful. So in other words, we can realize the category of like this trace, whatever category, as a full subcategory of something geometric. Okay?
Does the lemma say that the diagram is Cartesian?
It's not Cartesian, it's just this is commutative. Just commutative. Just saying that if you go this way, it automatically factors through. It's natural, there's a natural functor. Okay. So for this, I need to, yeah, I will specialize. So this is a very general setup. But maybe, yeah, but I will specialize later on. Okay. So maybe before giving examples, just do manipulating with these symbols for a while, and so. For this, I need to impose some some conditions on this morphisms F and M diagonal. So let me definition. I'll introduce a class of morphisms. I write this VR, called basically stands for vertically right adjoint. Be the class of morphism. Satisfying the following conditions such that it's this class of morphisms satisfying the following conditions. Satisfying for every Cartesian diagram, like a pullback diagram, we have the following. One, this F prime, because, okay, this, you can push, this class of morphism, we allow you to push forward to be stable under base change. So I can do this push forward for F prime, but I want this is, admits, it's right adjoint. Let me write as F prime upper dagger. So this, in the traditional things, daggers shrink, then this upper dagger, upper shrink pullback. Okay. I want this is preserve co-limits. Okay. 2 is once this is true, I can for every now I can consider if I have another, let's see, it's called G, Y prime, X no prime, this is G prime, this is F double prime. So because of this is like a three-functor formalism of shift theory, already there's a natural base change diagram associated to this Cartesian, right? Push forward, pull back, like dagger push forward, star pull back, commute with star pull back, dagger push forward. But I wanted this kind of this. When you apply the right adjoint, there's still some Cartesian diagram, something like that. So to write it, so you want some baked Chevalier map. Actually, I mentioned last time, it's kind of natural. So a priori, there's a natural map by a junction. So I hope what I wrote is correct. This is isomorphism for any G horizontal and also G prime nor dagger. Up. Oops. Okay, so basically it's, what I'm saying is if you take the right adjoint of this dagger push forward, it's still satisfying various base change with respect to all other morphisms. Okay. This is actually something very strong for this. And the third condition is basically satisfying some kind of projection formula. It's for any Z. The following diagram is commutative. So first of all, we have there's this exterior tensor product. Have this Y to Z. Then, oops, yeah. So then we have this D of X to Z. F times identity for dagger. Here I have D of X. Upper dagger times tensor with identity. So I wanted this diagram is commutative. Okay, so it's an exercise for you to check 2 plus 2 plus 3 actually would imply some kind of projection formula for this F upper dagger. Okay, some version of projection formula. All right, so similarly, so this is the definition of class of morphism. You can show this. This is very easy to show. This class is stable under base change composition. Okay. All right. So this is basically. Then similarly, we can define so-called similarly. It's a little bit like, for example, proper. So for example, instance this is certainly true is if this right adjoint, this F upper dagger is just F upper star, then that will be the case. This will be true, okay? So it's like some case of, let's say, proper is.
Is that more like smooth?
No, this is push forward.
The upper dagger being, upper shriek and upper star being.
No, this is a, dagger is like a lower shriek.
But upper dagger then is like upper shriek.
Upper dagger is like upper shriek. Oh, so it's a little bit like smooth, okay.
Does VR stand for like
Yeah.
vertically by your mind? What is VR?
If VR vertically right adjoint, yeah. Okay, so then it's more a little bit like smooth, okay.
Okay, thanks.
Yeah, all right. Similarly, one can define HR. It's horizontally right adjointable. So I will, I don't want to write down all the definitions you can imagine. It's 1, 2, similar 1, 2, 3. All right, so yeah, in the, for example, yeah, like as I said, the example is example here maybe is if this is true, if F upper dagger is just F upper, yeah, this is some example, but you allow more general situation, of course. All right, okay, so now let me state the proposition. Where what? 3 is upper dagger will be y to x. So it's yes, it's this. Thank you. I think it's this one. Is that good? All right. Right. Okay. So now let me just state the result. So this app's pretty, you see, we just, again, just manipulate symbols, but somehow I found it's useful before going to every concrete stuff. All right, so proposition. Let's make the following assumption. Stronger assumption, suppose fxy is horizontally right adjointable, okay? And again, we recall this is just you can do push forward. It's before diagonal, we have this diagonal. Before, when we talk about algebra object, we require this is it belongs to H. You can pull back, but I want this horizontally left right adjointable, and also recall we also have this pi x projecting to point is in H. All right, and the third one is suppose one can weaken the. Just right. The third assumption can be weakened, but somehow it's enough for our purpose. Suppose it's dx times x over y. This exterior tensor product is an equivalence. This exterior tensor product is an equivalence just for this particular object, x times x over y. All right, so then this map, let me write it again. This trace of f a ma to the y, y over y times y over Z is fully faithful admitting a continuous right adjoint. Okay, so that's a statement. So in other words, under this strong assumption on this morphism F and the map X to Y and this diagonal for X, then we could sort of realize this category for this trace category as the subcategory of the shifts on this space. All right. So the proof is actually not the it's applying this kind of Barbank-Lurie type argument, and it's kind of some abstraction of what the kind of argument given by Arnold last week. But so I don't want to discuss the proof, so let me just specialize this, put this symbol to some more meaningful mathematical objects to see what we get. I think that's a better thing. So we will specialize it step by step, gradually. The first thing we want to specialize is when Z is actually Y itself, and this map, two map G1, G2. Recall that to define this bimodule, we need this Z to get the two maps from Y. And I will take one of the Z is just Y. One map is just identity. The other is some kind of, let's say, some automorphism. Y. So then let's see, just this, what is this space? Of Z. So this is actually was already discussed before. This is kind of the twisted loop space of Y. Okay? So if phi is also the identity map, that's literally the loop space, I think was of Y mentioned last week. So this is a twist loop space. More special case is special cases. Let's see if I don't want to ask any question to Sarah. Okay. There's some interesting story 2 weeks ago when I was giving a talk, and Sarah says, okay, anyway. All right, so more special, okay, so even more specially, take Y to be the classifying stack of some group of G, and phi is like this Frobenius. Then this Y times Y over Z, the twist loop space, is just the G modulo the Frobenius conjugation. Sorry, this is G. So this is what, and in this particular case, if you take more specially, if you take X to be classifying space of, let's say, some Borel, then X times X over Y will be BB times BB over BG, but that's just the G mod B mod B. Okay, there's also, I think, Lucas mentioned something like this. So then this this important horizontal diagram is specialized to what actually Arnold mentioned last week. This horizontal diagram becomes basically this G mod B go to G. Frobenius conjugation by B, go to G. Conjugation by G. Okay? So this is this horizontal diagram get to this. And then if you apply this, all right. So then you can plug in any kind of shift theory you like. For example, theory of L-lattice shift, you get the the Lustig theory. Another thing for us is what we take is Y to be the B of the loop group, BLG, and also again phi is just of this Frobenius endomorphism. So let me just now do slightly better. Also encodes this monodromic version. So I will take this to be Frobenius. Yeah, okay. Frobenius. Then I will take X to be B of I plus. This is like this appropriate unipotent of Iwahori. And then if you just do this, you get just what I wrote yesterday. This horizontal diagram for the loop group. It looks like this. This is my delta. Yeah, by the way, in this case, okay, because I didn't talk about this, I'm sorry. I skipped details about this finite case, but I want to say a little bit more about this affine case, because it's really what we need. Is first of all, this delta, which is B I plus to I plus times I plus. This is actually, if you think about it, it's I plus torsor. Yeah, okay. This is this is I plus torsor. In some sense, okay, maybe not really torsor, but maybe. But anyway, this is a cohomological. Huh? Oh, sorry. Yeah, this is a diagonal delta. This is actually cohomologically pro-smooth. Okay, and because it's basically fibers like it's a B plus, it's a smooth group, and this turns out this is in this HR for the shift theory. Define. So one, of course, needs to prove something to say this is okay, but it's indeed okay. On the other hand, if you consider F, it's going to be B of I plus go to B of LG. So the fibers are looks like LG more I plus. But it turns out this is not improper. So if I just do BI, then I'll be in good shape. So if F was oh sorry, this is yesterday I didn't know by. So this is not, but this is not in VR. So in other words, actually you can't really, the map is not really, the problem in this map is, if this is BI, classifying stack to Iwahori to B of LG, the fibers are F and flag variety is improper. So actually it's vertically right adjoinable. But if I want to include all this, that actually accounts for unipotent version. But if I account to the Tame version, I wouldn't get, this is not, you can't just directly apply the formalism directly. So, but on the other hand, recall yesterday, we are not really want to consider the pullback of all shifts on here. We just want to just consider those monodromic shifts, okay? So actually what you can do is you can change the formalism a little bit. So actually this six-functor formalism is not this shift I start with. So what I really start with C is the following thing, is consider the pairs, is pairs T, a torus, act on a pre-stack. So this is actually my category, and this category admits all the finite product. And then in this category, you do have this, instead of consider the category, the formalism for just for shifts, you can consider formalism for monodromic shifts. You send, like, I will not write down this vertical map of horizontal, but just write X, go to X monodromic. Oh, maybe, sorry. Which by definition is just you'd consider the all possible monodromic shifts on T, which is actually a subcategory. It's actually an ideal inside D of T and then D of X. Oh, sorry, not D, shift. Okay, and now I will change this. I will change now. This my X will be Y. My Y will be this equipped with the action of T, but this action is trivial action. Yes.
How is there a functor from sheaves on X or sheaves
There's
on T?
no, there's no functor. It's action.
It's not an action?
No, shifts T acts on X, so shifts on T acts. Yeah.
I'm not thinking categorically. Sheaves on X is a module.
Yes, shifts. Yeah. Right. So then here I consider this T action, the natural T action, maybe T of K. Because the T of K is Ivahorian modulo property per unipotent. Now, if you remember this T action, it turns out this F becomes now this F, this BI, equipped with this action of TK, mapped to BG, equipped with trivial action of T, is vertically adjoinable. This is essentially if the non-properness is on this torus direction, but when you restrict to the subcategory of monodromic shifts, like push forward behaves like a proper push forward. So you will get this. Then we can actually apply this formalism. And then we get this following theorem. It's just the trace of maybe write because I've already changed this is like the Hochschild homology of this acton this bimodule, but this bimodule looks very similar with like the original thing. It doesn't, because Z is basically still Z is still just Y. So it's almost the same, except the module structure changes. It's not naturally multiplication. There's actually the module structure changed by this kind of Frobenius, and this is actually equivalent to the shifts on ISOC. Okay, we get this result. The proof is now it's basically fully faithfulness is this abstract thing. This is proposition. Yeah, maybe I should say more precisely. Fully fit the proposition, this abstract proposition, says that this Hausdorff homology maps fully faithfully to sheaves on this loop space of BLG. The Frobenius twist loop space, but this is just the sheaves on ISOC, okay, of G, maybe a tau version. This is fully faithful, but exactly the theorem yesterday afternoon says what's the essential image? Essential image is obtained by this. If you look at this diagram, it's exactly obtained by this. The essential image is, coming from this horizontal transform, and in this particular case, is literally just doing this map, pull push. Okay, and that's exactly what we identified yesterday as shifts and Tame. Okay, so that's we get at least the one side of the theorems to exactly realize this. Any questions so far?
Okay. Early in the formalism, okay, I guess most of my questions are about this external principal contour. It appeared early and needed to assume that it had a continuous right adjoint, and then later, a stronger assumption that it was just equivalence. So
Yes.
how do you prove these things?
How to prove why it's equivalence?
Yeah,
So, in this, first of all, it's fully faithfulness. This is pretty general. In most situation, that's okay. It's kind of a Kunis formula. It's most situation we encounter in everyday. That's okay. But yes, this condition is more essential. Is this? I think this was also mentioned last week in Arnold's talk. In general, this fails in general, but what you just need is for just this particular one, x times x over y, this holds, this diagonal holds. Then you will get this theorem. So, okay, now you are right, completely right. Now we really need to check is. Besides those maps, F and the diagonal are in VR, HR, we also need to check this is true. So there's a, thanks actually, maybe, so there's a, we need one more lemma. This is, and it turns out, if you think about this, actually false without adding this monodromic condition. And when you add it, essentially it's because you have this Schubert stratification. This was, I think this idea appeared.
2 copies of the space in the way?
2 copies of the space. So this idea actually appears, I think, also last week in various talks. You can write it in this way. So these stacks are essentially kind of discrete. So it's kind of on each strata, this is actually just the equivalent to monodromic shifts on torus. This is not canonical, but you need to do some, make some choice, choose a lifting of element in the F and Y group. And then reduce to the following thing. So reduce to show the following thing. This is equivalent. And this is but recall what are the monodromic shifts on torus. These are just the shifts generated by character shifts, character local system. But the whole point is the character local system on product torus is the exterior product of character local system torus. So I stop here. I think that's.